This video talks about four very important charts that we use when we're talking about statistical process control of a process. And so I just want to go through and give you an overview of one, how to make the charts, and then also how to interpret the charts. The first chart that we're looking at is the average. And if you're using the Stevenson Operations Management textbook, this comes out of the section in statistical process control. The first one that we go to is what they call an X-bar chart. And I think you remember from probability that X-bar really is the average. And so in this case, what we have is we're trying to make sure that over time that our process is what we call under control. And when we're talking about being under control, what we mean is that we don't have any trends in here, that we don't have any individual points that are what we would consider out of bounds. And then we're kind of managing the overall variability. So in this case, we have 5 different samples, or 5 different days, if you will. And on the 5 different days, we have sampled 4 different items. Say we were looking at the number of fluid ounces in a soda that was being put into a can. And so every day we go in and we sample 4 times, and we come up with the average for that day. So what we're looking at right now is over a 5-day period of time, what is the average amount of soda that actually ends up getting put into a can when we're talking about the number of fluid ounces. So we've taken the average each day, I'll put it up here, of each one of the 4 samples that are in there. All right, again, 5 days, each day we sample 4. And you can see that each day we have calculated the average for all of them. So the system average is really the average of all of the averages. So over these 5 days, here are the individual days, what we sampled, but this is what the system also tells us. We can also take and calculate the standard deviation of all of these items by left-clicking and highlighting all of them and using the stdev.s function. So if you type in stdev.s, and the reason it's .s is for a sample instead of a population, and the reason it's a sample is we didn't test everything, we just tested 4 items each day, and we left-click and we drag for all of that stuff, we can go ahead and hit enter, and our system standard deviation is 0.02. The number of items that we are looking at each day is 4, right? We're just sampling 4 items each day. And then finally, the last one is the Z. Z is the number of standard deviations that we're normally looking at, okay? Usually for a 6 sigma, we're looking for 3 standard deviations above the mean or 3 standard deviations below the mean. However, there are times whenever we are taking that information and we're going to look at calculating standard deviation just a little bit differently. However, you will see in a lot of books and a lot of organizations that the standard Z value truly is 3 standard deviations above plus 3 standard deviations below, which would be 6 standard deviations. All right, the reason these matter to us is that we want to calculate for us the overall standard deviation from our sample. Okay, now we did the system standard deviation, and that system standard deviation, we now can go back and say, just to hold on a second, we have also sampled more, right? So the sample standard deviation is the system standard deviation divided by the square root of the number of items in a sample. So I'm going to highlight this so you can look at it. It is the system standard deviation, cell B10 here, divided by the square root of B11, and B11 is 4. Okay, so that's how we came up with 0.01. Now the next thing that we do is we want to establish an upper control limit and a lower control limit. The upper control limit is what is our system average, we've already calculated that, plus 3 times the system or the sample standard deviation. So we have the system average plus 3 times the sample standard deviation. That gives me an upper control limit. Now for a lower, I have a typo right there. This is my lower control limit, and the lower control limit is the average minus 3 times the standard deviation. So we have the data here now to come over and fill in an X-bar chart. I have moved over and I've put in our 5 samples. You can see from the 5 samples that the sample average is from that day, okay? So 12.1 was day 1, 12.12 is day 2, you get it. Upper control limit, we're going to go ahead and paste in here, do a paste special so it removes the formulas, what the upper control limit is. The lower control limit, same exact thing, and the average 12.11 has already been calculated and we're pasting it in there. Because what I want you to be able to do is I want you to be able to put in a chart that shows an upper line, or upper control limit, a lower control limit, the average, and then I would like to see a scatter plot here of the individual points. All right, and the way you're going to do that, if you highlight all of your data and you go up to Insert, and you can choose any one of the charts, but I'm going to left click on Insert Line Chart, and whenever the data shows up, at this point, what we have is we have different series and samples, and what ended up happening is our upper control limit and lower control limits, they're down here on the X bar. We really are, on the X axis, they should be on the Y axis. So if I right click on the data or on this chart, one of the things that I have is to select data. Select data, and you can see all of the items that I would like to see on my Y-axis are actually on the X-axis. So I'm just going to click on switch row or column. Now, because of Excel puts this in there for you automatically. Yours may already be over here on the left, so you may not have to do this step. But I'm going to left click because what I want to be able to do is I want to be able to have on this side the average, sample average, UCL, and LCL. Sample is nothing more than the number of the sample, so that's not important, so I'm going to left click it so it goes away. Okay, I'm going to click OK at this point, and when we get here, now we see everything is in a line format. That's not what I want. I want this actual sample average to be a scatter plot. So if I go up to change chart type, I left clicked on it, and I come down to combo and left click on combo. When I click on combo, it says, how do you want to put these things in here together? Well, I want the sample average to be a scatter plot. I want the upper control limit to be just a regular line, LCL to be a line, and the average to be a line. Okay, I'm going to click OK here, and you will see at that point that everything has come back in now to where we can, it looks like what I was already had put in there before. If you left click on this title, you can actually change this down to an X bar chart. All right, what the X bar chart shows me is on average, this is what the system typically does. The system typically puts in 12.11 ounces of soda. If I want it to be back down to 12.0, I need to do something, right? Because I'm normally at 0.1 ounces above what I would like to be. So that immediately tells me that, if I want it to be 12.0, I need to dial in my process to where it brings it down. It also shows me here that every day whenever I'm sampling, that I have some days that it's low, some days that it's high, some days it was actually exactly on it. And there appears to be, and we may not have enough data yet, but there appears to be this overall cycle, something going on maybe that we have a cycle in here that we need to look at. However, it also shows us that we don't ever have any points that are above the control limit or, above the control limit or below the control limit. So any of those days, if we had something to where we were way out of bounds, we would need to go and take and check to see what's going on. We also don't see a trend where we start down here and then over time we just slowly keep, trending out of bounds. So what we're looking for in an X bar chart is on a daily basis or on a sample basis, what's happening with our process? Is it increasing? Is there too much variability in it, right? Or do things seem to be under control? All right, so that's the idea on statistical process control chart for us for an X bar chart. The next thing that we talk about is what is an R chart. And an R chart says, what about my range? On a daily basis, looking at each one of my samples, do I have some samples that are really low and other samples that are too high? So we're looking at trying to calculate the range. So down here under range, what we have is the max of this day's sample minus the min of this day's sample. And so you can see from looking at it, 12.11 happened a few times. 12.8 is the lowest. 0.03 is the range for that day. And if I calculate it for each one of the days, I can do an overall average for all of the days in there. Okay? Now, for doing my upper control limit, if you look at table 10.3 of your textbook, 10.3 is it's a derivation of the normal distribution. And there may have been a time in the past when you went in and you looked at the what we called a Z table. And in a Z table, it said, how many items did you sample and how many standard deviations are you looking for? So in this one, what we're looking up inside of table 10.3 is whenever I have a sample of 4, right, when n equals 4, and I look through at the table at column D4, column D4 says that that value is going to be 2.28, okay? And whenever I look up D3 in the same table, it says that that value is going to be 0. So to calculate the upper control limit and, again, lower control limit, for my R chart or my range chart, I take the value that comes from table 10.3, 2.28, and I multiply it times the range. So I'm going to go here. I have 2.28 times the range. So my upper control limit is 0.105. Same thing for the bottom. Lower control limit, we have the range times the lower control limit. All right, let's take these values and swap them over. Sample 1 through 5, range is 0.03, 0.05. You see how these have just been moved over. Upper control limit, we calculated. Lower control limit, we calculated. Average, we calculated. And then we put in a range chart that looks exactly like the X bar chart, except now we're saying how much variability is there on a daily basis, right? And I don't want to have too much variability on a daily basis. So with that, we have our current average. We see exactly what the range was each day, what our upper and what our lower is. So again, hopefully this makes sense to you whenever you're putting in the range chart. Now let's change just a little bit and say, what about those times whenever I'm doing inspections and I'm really interested in the proportion of the items where I have a defect? All right, so on this one we have 20 days in a row where we've gone in and inspected 100 items each day. And when we're looking at these defects, what I'm looking at in particular is the proportion, right? What proportion did we have a defect each day? So you can see over here on the chart that I have calculated the proportion by taking the number of defects and dividing by the number that were inspected. All of this comes in here. Now let's go down below and look at the overall proportion. The overall proportion of defects is the total number of defects by the total number of observations. All right, I've put all the defects here, the number inspected that day. You can see that I have summed up all of the defects in this column or in this cell. So there were 220 defects out of the summed up number that were inspected of 2,000. And whenever I take and divide 220 divide by 2,000, I end up with 0.11. All right, now the next one is the estimated standard deviation. Estimated standard deviation is done a little bit differently than what we've done in the past. It is the proportion of standard deviations multiplied by the proportion that were not defected divided by the n, all right? And in this case, and we take the square root of that. So let's come in here. Let's take a look at it. It says take the square root of the proportion that were errors or defects multiplied by 1 minus the number that were defected divided by n in this case is the number that we sampled each day, which is 100. So in this case, our standard error or estimated standard error is 0.03. Have an upper control limit and a lower control limit. And I mentioned to you before that oftentimes companies will go with a Z of 3. Again, it comes from the Six Sigma idea where there are 3 standard deviations above and 3 standard deviations below. It may be different for the company that you work with. However, in this case, the textbook is going with a Z of 3. So what we have is take our proportion, add 3 times our estimated error that comes from the standard deviation. Going to go again for the lower control limit. You can see again, it is the proportion minus 3 times the standard error that comes out of it. We move these values over once again. I showed you where we got the proportions. They're for each day. Upper control limit, we just calculated. Lower control limit, we have calculated. Average is here. And the reason that these numbers here don't look exactly like the others is because the number of significant digits wasn't correct. So once we put these together, this P chart now starts to tell us, okay, what proportion of the ones that we're sampling are out of bounds, okay? So over 20 days here that we have sampled, we have one day where things don't look right, okay? One day something's going on, and we may need to go and investigate this and see what's going on. I didn't mention it before, but I should have, but there is a concept that we refer to as bias. And a bias would be any time where we have more data points below the mean or more data points above the mean. So it's important for us to look at the bias. You know, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 that are below and one that's on it. So that means that we only have 1, 2, 3, 4, 5, 6, 7 that are above. In this case, we probably need to start looking at our process because we have more that are below or a negative bias in that case than we have positive bias. It looks like the days that where we have a positive bias, they seem to be further away from the mean. So again, we may need to check our system to see what's going on that causes us to get in this situation again. All right, last chart that we're going to talk about here is a C chart. And the C chart, again, is referring to the number of occurrences. Something has happened. We've got an item that's dented or something along those lines. There's a chip in it. And so as we're going through and we're looking for a C chart, what we have once again is we have the number of observations. In this case, we have 18 days that we've looked. And when we've inspected, here are the number of occurrences that we've received each day when we've gone through it. We sum up the number of occurrences. All right, there's 45. To calculate the average, what we're going to do is we take the total number of defects that we have found by the total number of times that we have sampled, in this case 18. So the average number of occurrences that we get over the 18 days is 2.5. We're looking for an upper control limit calculation where we take the average that we get each day times z, and I mentioned to you before that's 3, and that's what we're going to use again here, divided by the square root of the number of errors that we have. So let me put it up here for you. So we start off with the average number of occurrences plus 3 times the square root of the number of occurrences. That is 7.24 for the upper. And when we do it for the lower, we end up with a negative number. And it doesn't make any sense for us to have a negative number of defects. So anytime you calculate a number of a lower control limit and it comes out negative, go ahead and make your lower control limit a 0. All right, let's transfer this information over here. Samples, you see that we have the number of occurrences that we just brought over, upper control limit that we just calculated, lower control limit of a 0 since we were negative, and then the average. So on our C chart, now on the C chart, you see here we're kind of squished. The lower limit's not as big. However, you can see that from looking at this, we have a nice kind of scatter plot. Doesn't seem to be much of a cycle. Seems to be almost as many that are above as there are below for these defects. And we don't have anything out of bounds. So once again, the important part of this video is to look at statistical process control, come up with the 4 charts that we use for statistical process control, with the X-bar chart where we're looking at the average and seeing, if we have bias, if we have some sort of trend, if we have a cycle that's associated with it, or if there's just too much dispersion where we're bouncing around. Similarly, the R chart looks at the range, how much difference is there between our max and our min. The P chart is a way for us to look at proportions of the number of items that are being inspected on a day. And finally, the C chart, where we're just looking at the number of defects in the sample that we've gotten. Hopefully this makes sense. You know how to be able to do each one of these charts now. Good luck, and let me know if you have any questions.